This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I have four super handouts for you today. If you haven't gotten them yet, feel free to just sit down. We're going to probably make it a point, because there's so many people in the class, to just hand them out while I start lecturing. This way we don't have this big bottleneck of people trying to get in by 11 o'clock. The four handouts are posted to the webpage. The mailing lists were created last night, and I just looked at it this morning, and there were 245 email addresses on it, so it looks like it's working. I haven't sent anything to the email list yet, but I will just contrive a message later this afternoon and send it to everybody. And if you don't get that by Monday morning, when I make an announcement, say, if you didn't get that message, let me know. Then I'll investigate as to why you're not on it. SCPD students, I'm not sure that you're actually on the mailing list yet. That system runs a little bit differently, and usually they push your email addresses onto the mailing list a little bit later. I'm not sure why, but so if you don't get an email over the course of the weekend, then just let me know, and I'll see what I can do to fix it. I'll also post announcements to the webpage so that you at least can get them. What I want to do is I want to start talking about the low-level memory mechanics, so that you understand how data, things as simple as booleans and integers and floating point numbers and structs and classes, are all represented in memory. It's very interesting, I think, to understand how everything ultimately gets represented as a collection of zeros and ones, and how it's faithfully interpreted every single time to be that capital A, or that number 7, or pi, or some struct that represents a fraction, things like that. And we'll just become much, much better C and C++ programmers as a result of just understanding things at this low of a level. So for the moment, C and C++ are the same language to me. So let's just talk about this. Let me just put a little grid up here of all the data types that you've probably dealt with. You've probably dealt with bool. You've probably dealt with char. I'm sure you have. You may not have dealt with the short, but I'll put it up there anyway. You've certainly dealt with the int. You've certainly, well, maybe not dealt with the long, but let's just pretend you have. You've probably seen floats. You've probably seen doubles. And that'll be enough for me, enough fodder for the first 10 minutes here. These three things right there are certainly related. They're all intended to represent scalar numbers. Obviously, this represents a true or a false. This represents, in our world, one of 256 different characters. We usually only pay attention to about 75 of them, but nonetheless, there are 256 different characters that can be represented here. These are all numeric. These take a stab at trying to represent arbitrarily precise numbers. Okay. The character is usually 1 byte in memory. At least it is in all C and C++ program compilers that I know of. This is typically 2 bytes. The int can actually be anywhere between 2 and 4 bytes. But we're going to pretend in this class that it's always 4 bytes. Okay. The long, for the time being, is 4 bytes of memory. There is another data type, which isn't really common enough to deserve to be put on a blackboard, called the long, which gives you 8 bytes of memory to represent really, really large decimal numbers. They'll come up later on, but I'll talk about them if I ever need to. The float is 4 bytes. It somehow tries to take 4 bytes of memory and represent an arbitrarily precise number to the degree that it can, given that it's using a finite amount of memory to represent a number that requires an infinite amount of precision sometimes. And a double, I've seen them 10 and 12 bytes on some systems, but we're just going to assume that they're 8 bytes. Now, that's the most boring spreadsheet you could possibly introduce a class with, but my motivation is that I want to uncover what the byte is all about and how 4 bytes can represent a large frame of numbers, how 8 bytes can represent a very large set of numbers, and actually do a pretty good job at representing numbers precisely enough for our purposes. So forget about bytes for the moment. I'll go back to the bool in a second because it's kind of out of character as to how much memory it takes. But I'm interested at the moment in what is less commonly called the binary digit, but you've heard it called the bit. And EE students and those who enjoy electronics think of the binary digit in terms of transistors and voltages, high and low voltages. Computer scientists don't need to view it that way. They just need to recognize that a bit is a very small unit of memory that can distinguish between two different values. EEs would say high voltage, low voltage. We don't. We actually just assume that a single bit can store a 0 or a 1. Technically, a Boolean could just be mapped to a single bit in memory. It turns out it's not practical to do that. But if you really wanted to use a single bit to represent a Boolean variable, you could engineer your compiler to do that. Okay? Bits are more interesting when they're taken in groups. If I put down 8 bits here, I'm not even going to commit to a 0 or a 1, but I'm going to draw this. This isn't 0 over 1 as a fraction. This is me drawing 8 bits. And let me just draw one over here so I have some room. And put a little box around each one of them in this binary search way. Okay, and I have this big exploded picture of what we'll draw several times to represent a single byte in memory. Now, the most interesting thing to take away from this drawing is that this little box right here can adopt one of two values, independently of whatever value this box chooses to adopt, etc. In fact, there are 8 independent choices for each of the bits. I'm assuming that makes sense to everybody. Okay? That means that this, as a grouping, a byte of memory with its 8 bits that can independently take on 0s and 1s, can distinguish between 2 to the 8 or 256 different values. Okay, and that's why the ASCII table is as big as it is. Okay, 65 through 65 plus 25 represents the alphabet. I forget where lowercase a starts. But every single character that's ever printed to the screen or printed to a file is backed by some number. I know you know that. When you look in memory to see how the capital A is represented, you would actually see a 1 right there. I'm sorry, I forget where it is actually. A 1 right there and a 1 right there. I'll draw it out and explain why that's the case. Because capital A is backed by the number 65, we don't put things down in decimal in memory. We put them down in base 2. Okay, because that's the easiest thing to represent in a bit-oriented system. Okay, does that make sense to people? Okay, so if I say that the capital A is equal to 65, you have to stop thinking about it as 65. You have to think about it as some sum of perfect powers of 2. So it isn't 64. It isn't 65, rather. It's actually 64 plus 1. 1 is 2 to the 0th. A 2 is 2 to the 1st. There's none of that. 4 is 2 to the 2nd. 8 is 2 to the 3rd. 16 is 4. 32 is 5. 64 is 6. This is actually 2 to the 6th plus 2 to the 0th. Makes sense? Okay. As far as the representation in a box like this, if you went down and actually examined all the transistors, okay, the 8 that are laid side by side in a single character byte of memory, it would look like this. And in order to recover the actual decimal equivalent, you really do the power series expansion, where you say there's a contribution of 2 to the 6 because it's in the 6th, counting from 0 from the right, the 6th position from the end of the byte. This contributes 2 to the 0th. You can look at it as having contributions of 2 to the 1st and 2 to the 3rd and 2 to the 7th that are weighted by a 0 as opposed to a 1. Okay, that makes sense to people? Okay, so that's good enough for characters. Let's graduate to shorts. Some people are very clever when they use shorts. A lot of times, if you know that you're going to store a lot of numbers and they're all going to be small, they'll go with an array of shorts or a vector of shorts, knowing that there really will be some memory savings later on. The short, being 2 bytes, just means that 2 neighboring bytes in memory would be laid down. Those are the 2 bytes at the moment. Would be laid down, and the 2 to the 16th different patterns that are available to be placed in that space can distinguish between 2 to the 16th different values. That makes sense to people? Okay. So I'll just make this up. I'll put lots of zeros over here, except I'll put 1 right there. Did I put too many? Yes, I did. And this is a wide bit. Okay, so as far as the number that represents, I should emphasize that technically you can map that pattern to any number you want to as long as you do it consistently. But you want to make the computer hardware easy to interpret. This place right here means that there's a contribution of 2 to the 0th or 1. There's a contribution of 2 to the 1st, contribution of 2 to the 2nd. So there's a 2 and a 4 that are being added together. 2 to the 0th, 2 to the 7th, 2 to the 8th, 2 to the 9th. Okay, so there actually is a contribution of 2 to the 9th, which is 512. So this really is the number that's represented by this thing. It would be 512, 516, 518, 519 would have that bit pattern down there. Okay, does that make sense to people? If I have another one, oops, I don't want that there. I have 1 0 followed by all ones and all ones. Okay. I know that if this had been a 1 right there, then that would have been a contribution of 2 to the 15th. Does that make sense to people? Okay. 0 followed by all ones in binary is like 0 being followed by all 9s in some sense in decimal. It's 1 less than some perfect number that has a lot of zeros at the end. Okay? Does that make sense? But think about you have a binary odometer on your car and you want to take a mile off. Okay? Because you're at, let's say, 1 followed by 15 zeros. If you back it up, you expect all of these to be demoted not to 9s but to 1. So as far as a representation is concerned, it's 1 less than 2 to the 15th. Make sense? And that number is 2 to the 15th minus 1, which I'm not going to figure out what it is. Okay? You get the gist of what's going on here? Okay. So that's enough. There is a little bit to be said about this bit right here. If I wanted to represent the numbers 0 through 2 to the 16 minus 1, I could do that. Okay, that's 2 to the 16th different values. I don't want to say that negative numbers are as common as positive numbers, but they're not so uncommon that we don't want to have a contribution of the mapping to include negative numbers. So what usually happens is that this bit right there has nothing to do with magnitude. Okay, it's all about sign, whether or not you want a 0 there because it's positive or a 1 for negative. And that's usually what 0 and 1 mean when they're inside a sign bit. Make sense? Okay. So if I write down this, and I have, let's say, 4 zeros followed by 0, 1, 1, 1, okay, that's a 7. If I put all zeros there, it happens to be a 7 that hogs a little bit more memory. Okay, it was a 7 character initially, and now it's a 7 short. I could argue that this would be the best way to represent negative 7. And you can look at it, and you can recover the magnitude based on what's been drawn, and then just say, look all the way to the left and say that 1 is basically the equivalent of a minus sign. That would be a fine way to do it if you wanted to go to the effort of actually always looking at the leftmost bit to figure out whether it's negative or not. The reason it's not represented this way is because we want addition and subtraction to actually follow very simple rules. Okay? Now let me just be quite obtuse about how you do binary addition, not because it's difficult, but because it's interesting in framing the argument as to why we adopt a different representation for negative numbers. Let's just deal with a 4-bit quantity, okay? And I add a 1 to it. Okay? Binary addition is like decimal addition with more carries because you just don't have as many digits to absorb magnitude. So 1 plus 1 is 2, but you write that down as 0 when you carry the 1. You do this. And that's how 7 plus 1 becomes 8. Okay, I'm imagining everybody followed that. However, I want the computer hardware and its support for addition and subtraction to be as simple and obvious as possible. So what I'd like to do is have the number for positive 7, when added to the representation for negative 7, to very gracefully become all zeros. Does that make sense? Well, if I use the same rules, zeros followed by 0, 0, 1, 1, 1. This is 4 of them. This is 8 of them. and I want to add that to 7 zeros, followed by 4 zeros, 0, 1, 1, 1. Let's put a 4 in there. Let's put an 8 in there. If I follow the same rules, and think about, I mean, it's not like the hardware is what's propagating electrons around and voltages around to emulate addition for us. If we want to follow the same rules, we would say, okay, well, that's 2, carry the 2. That's 3, it's 2, carry the 1. That's that. Let me just make sure I don't mess this up. 7 plus 7 is 14, so it would be that right there. Okay, and then you'd have 11 zeros followed by a 1. If I really just followed the algorithm I did up there blindly, that's how I would arrive at 0. Okay, and that's obviously not right. If I were to argue what representation that is, if this is negative 7, then this has to be negative 14. That's not what 7 plus negative 7 is. Okay, so that means that this right here, as a negative number, has to be engineered in such a way that when you add this to this using the normal binary ripple add pattern, okay, that you somehow get 16 zeros right here. Okay. It's easier to not worry about how to get all zeros here. It's actually easier to figure out how to get all ones here. So if I put down 4, 5, 6, 7, 8, 1, 2, 3, 4. Let's mix it up. Let's put the number 15 down. And I want to figure out what number or what bit pattern to put right here to get all ones right here. Then you know you would put a bit pattern right there that has a 1 where there's a 0 right here and a 0 where there's a 1 up here. Okay? This right here is basically 1 mile away from turning over the odometer. Okay? Does that make sense? Okay. So what I want to do is I want to recognize this as 15 and wonder whether or not this is really close to negative 15. And the answer is yes, it is. Because if I take this right here and I invert all of the bits, if I add 1 to that number right there, do you understand I get this domino effect of all of these 1s becoming zeros? I do get a 1 at the end, but it doesn't count because there's no room for it. It overflows the 2 bytes. Okay? So this right here would give me this 1 that I don't have space to draw because I'm out of memory, all the way down. So what I can do is, rather than just changing this right here to be a sign bit, I can take the forward number, the positive 15, invert all the numbers, and add 1 to it. Okay? Does that make sense? And that's how I get a representation for negative 15. This right here, this approach, it's what's called one's complement. It's not used because it screws up addition. This notation for inventing the representation of the negative is what's called 2's complement. Okay? It's not like you have to memorize that, I'm just saying it. And this is how you get all zeros. This is positive 15. This is negative 15. That is 0 right there. Okay? Does that make sense? The neat thing about 2's complement is that if you have a negative number and you want to figure out what negative of negative 15 is, you can follow the same rules. Invert all the bits. There, 1. And add 1 to it. Okay? And that's how you get positive 15 back. So there's this nice symmetry going on with the system. Okay? Make sense? Okay. Now why am I focusing on this? It's because you have to recognize that certainly in the world of characters and shorts, which is all we've discussed so far, that every single pattern corresponds to some real value in our world. Okay? Characters, it's one of 256 different values. We can fill in the ASCII table with ampersands and A's and periods and colons and things like that and have some unique integer be interpreted as a character every single time. As long as it's constant and it always maps to the same exact pattern, then it's a value mapping. As far as shorts are concerned, I could have used all 16 bits to represent magnitude. I'm not going to do that because I want there to be just as many negative numbers represented as positive numbers. So I do, in fact, dedicate all of the bits from that line to the right to magnitude, okay? And I use the left one, the leftmost bit, to basically communicate whether the number is negative or not, okay? That means that since there are 2 to the 16th different patterns available to a 2-byte figure, that the short can distinguish between that many values. Rather than having it represent 0 through 2 to the 16 minus 1, I actually have it represent negative 2 to the 15, I'm sorry, negative 2 to the 14 through 2 to the 14th, I'm sorry, negative 2 to the 15th through 2 to the 15th minus 1. Does that make sense? And everything's centered around 0. So I have just as many representations for negative numbers as I have for positive numbers. Okay? Make a sense? Okay. So let's start doing some really simple code. Not because it's code you'd normally write. Sometimes you do, not very often. But just to understand what happens when you do something like this. I have a char variable, ch, and I set it equal to capital A. And then I have an int variable called I. Actually, let me make it a short. S, and I set it equal to ch. You don't need a cast for that. What you're really doing is you're just setting s equal to whatever number is backing ch. There's a question right there?
Yeah, you said that when you turn around the negative, you get everything back. That's different from your original.
It shouldn't have been. Oh, I'm sorry, I inverted the bit pattern, and then I said you would add 1 to this, and I just didn't change the bit in the drawing. Where'd you go? I just saw, okay. So I didn't add 1 to this yet. But in the conversation at the time, I thought it was clear. Okay. Does this make sense to people? Okay. There's certainly that's going to compile and it's going to execute. And based on the other 7 boards I've drawn in, you should have some idea as to what's going to happen in response to this line. Printf is the equivalent of a cout statement, but it's in pure C. And if I want to print out a short, actually, let me just use cout. Less than s is less than ENDL. In response to that, I expect it to print out the number 65. So to the console, I would expect that to be printed. Why is that the case? Because the declaration of CH doesn't put a capital A there. It puts the integer value that backs it there, which I will draw as decimal. You know that it's really 1s and 0s. And so when time comes for you to assign to S, what happens, in order to achieve the effect of the assignment, it will copy this bit pattern, and this is what it really does electronically. It just replicates whatever bit pattern is right here onto that space right there. It smears these bits onto this little byte like it's peanut butter and puts a 65 down there. And all the extra space is just padded, in this case, with zeros. And so that's how 65 goes from a 1-byte representation to a 2-byte representation. Does that make sense? I simplified this a little bit. When I put a 65 down here and smear a 65 in there, I happen to know that the leftmost bit is a 0 there. It's a positive number, so that shouldn't surprise you. Okay? Does that make sense to people? What happens if I do the opposite direction? I do this. Int, I'm sorry, we're not at ints yet. Short, completely new program. S is equal to, I'll say 67. And I do this. It compiles, there's no casts needed. As far as how the 67 is laid down, it's 0, 1, 0, 0, 0, 0, 1, 1. It's 2 more than 65, obviously. It has an extra byte of all zeros, and this is S. So when CH gets laid down in memory, and it's assigned to S, 2 bytes of information and 16 bits cannot somehow be wedged economically into an 8-bit pattern. So what C and C++, and many programming languages for that matter, do is they simply punt on the stuff they don't have room for. And they assume that if you're assigning a large number to a smaller one, and the smaller one can only accommodate a certain range of values in the first place, that you're interested in the minutia of the lower bits. Does that make sense to people? So what happens is it replicates this right here and it punts on this, and this is how, when you do this right here, okay, you go ahead and you print out a C. Make sense, everybody? Okay. Now, I've kind of evaded the whole negative number thing, but negative values don't work too well with characters because unsigned cars, most characters are unsigned, so you actually do get all positive values with the representations. You know enough about shorts to know that they're 2-byte figures. I've already told you that longs and ints, at least in our world, are 4 bytes. They're just a 4-byte equivalent of a short. So let me deal with this example. I go ahead and I do a short s is equal to, I'll just say, let me write it this way. No, I'll just write it as 2 to the 10th plus 2 to the 3rd plus 2 to the 0. That, of course, is not real C, but I'm just writing it because I want to be clear about what the bit pattern for that number is. So just think about whatever number that it adds up to as being stored in S. Okay. This is 2 to the 8th, 2 to the 9th, 1, 0, 0, preceded by all zeros, lots of zeros, 1, 0, 0, 1. If I take an int I and I set it equal to S, the same argument that I made in the car to short assignment can be taken here, and this is how, and this is somehow less surprising because both of them represent integers. This is all zeros, lots of zeros followed by 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1. And that's why you just have a lot more space to represent the same small number. Okay? Trick question. If I set int I equal to, I have 32 bits available to me to represent pretty big numbers. So I'm going to do this. 2 to the 23rd plus 2 to the 21st plus 2 to the 15th plus, let's say, 7. Okay? And I'm being quite deliberate in my power of 2 representation of these numbers because 7 always means that at the bottom. Okay? 2 to the 15th means there's a 1 right there. 2 to the, actually, let me change this to 2 to the 14. Make this a 0, 1. 2 to the 21st, this is 2 to the 24th, 2 to the 23rd, followed by zeros, all zeros right there. So that's more or less what the bit pattern for that as a 4-byte integer would look like. I go ahead and I set short s equal to I. You could argue that, wow, that number's so big it's not going to fit in the short. Okay, and so you might argue, well, maybe we should try and come as close as possible and make S the biggest number it can be so it can try really hard to look like this number. And that's not going to happen. Okay, it's going to do the simplest thing. Remember, this is implemented electronically, and every single example over there has more or less been realized by just doing a bit pattern copy. Okay, if you're writing this way, you probably know that you're going and taking a 4-byte quantity and using it to initialize a 2-byte quantity. So, lay that down. This is S. And all it does is say, you know what, I have no patience for you right there. You're out. I'm just going to copy this down. Okay? And so I do this, followed by lots of zeros, followed by lots more zeros, followed by 1, 1, 1. And I print out S. I'm going to get the number that is 2 to the 14th plus 7. Does that make sense to people? Okay. So let me go back and do one more example before I move on to floating point. Oh, yeah.
Initially, you had 2 to the 15th.
Right. It's actually confusing as to what happens. It certainly is. I actually don't know what happens when what is a magnitude bit actually becomes a sign bit. I have to say, I certainly should know what happens, I just don't, which is why I gracefully said, oh, I have an idea. Let me just change this to 2 to 14th. I'll actually run an experiment after lecture, and I'll just mail the class as part of this email that everyone is getting today. Okay, yep?
The other way around, if you have a signed short and you're putting it in.
Well, it'll always preserve sign, and that's the very example I'm going to do right now. Okay? Suppose I did this. short s is equal to -1. Totally reasonable. Do any of you have any idea what the bit pattern for that would look like? And you can only answer if you didn't know the answer prior to 11 a.m. today. Okay? I want to be able to add 1 to -1 and get all zeros. Okay? Does that make sense? So the representation for this is actually all ones. In fact, anytime you see all ones in a multi-byte figure, it means it's trying to represent -1. Why? Because when I add +1 to that, it causes this domino effect and makes all those ones zeros. Does that make sense? So to answer your question, int I equal to s, logically I'm supposed to get int to be this very spacious representation of -1. It actually does use the bit pattern copy approach. It copies these. I've just copied all the magnitude, okay, and by what I've put down there, it's either it's either a very large number or it's -1. We're told that it's -1 right there, okay. What happens is that when you assign this to that right there, it doesn't just place zeros right there, because then all of a sudden it would be destroying the sign bit. It would be putting a 0 in the sign bit right there. Make sense? So what it really does, and it actually did this over here, but it was just more obvious, is it takes whatever this is in the original figure and replicates that all the way through. If these would have otherwise been all zeros, and I want to be able to let this one continue a domino effect when you add a positive number to a negative number, you technically do what's called sign extend the figure with all of these extra ones. So now you have something that has twice as many dominoes that fall over when you add +1 to it. Okay? Does that make sense? Okay. So there you have that. As far as character shorts, ints, and longs, they're all really very similar in that they have some binary representation in the back representing them. They happen to map to real numbers for ints, longs, and shorts. They happen to pixelate on the screen as letters of the alphabet, even though they're really numbers, very small numbers in memory. Okay? But the overarching point, and I actually don't want you to memorize too much of this. Like if you know that 7 is 111 and you know that all ones is -1, that's fine. I just want you to understand the concept. With integers, I have 4 bytes, I have 32 bits. That means I have 2 to the 32nd different patterns available to me to map to whatever subset of the full integer range I want. The easiest thing to do is to just go from 2 to the -31st through 2 to the +31st minus 1. Okay? There's 0 in the middle, that's why it breaks it symmetrically a little bit. When I go and start concerning myself with floats, you're probably more used to doubles, but this is just a smaller version of doubles. I have 4 bytes available to me to represent floating point numbers, integers with decimal parts following it in any way I want to. This isn't the way it really works, but let me just invent an idea here. Pretend that this is how it works. Without drawing any boxes yet, I could do, let's say I have a sign bit. I'll represent that up here as a plus or minus. And if I have 32 bits, you'd by default think about being some contribution of 2 to the 30th, 2 to the 29, all the way down through some contribution of 2 to the 0. And I'm just describing all the things that can adopt zeros or ones to represent some number. Okay? But I want floats to be able to have fractional parts. So let me move in the fractional direction and say, you know what? Why don't I sacrifice 2 to the 30th? Oops. And let 1 bit actually be a contribution of 2 to the -1st. I'm just making this up. Well, I'm not making it up. This is the way I've done it the last 7 times I've taught this. But I'm moving toward what will really be the representation for floating point numbers. If I happen to have 32 bits right here, and I lay down this right here, that's not the number 7. I'm sorry, that's not the number 15 anymore. Now it's the number 7.5. Does that make sense? Okay, well, floats aren't very useful if now all you have are integers and half integers. So what I'm going to do is I'm going to stop drawing these things above it because I have to keep erasing them. Let's just assume that rather than the last bit being a contribution of 2 to the negative first, let that be a contribution of negative 2 to the negative first, and let that be a contribution of 2 to the negative 2. So now I can go down to quarter fractions. Does that make sense? Well, what I could do is I could make this right here the contribution of 2 to the 0, 2 to the negative 1, 2 to the negative 2, 3, 4, 5, 6, 7, 8, 2 to the negative 9. And if I wanted to represent pi, I'm not going to draw on the board because I'm not really sure what it is, although I know that this part would be 1, 1. Then I would use the remaining 9 bits that are available to me, okay, to do as good a job using contributions of 2 to the negative first and 2 to the negative third and 2 to the negative seventh to come as close as possible to 0.1415, whatever it is. Okay? That makes sense, I'm assuming? It is an interesting point to remember that because you're using a finite amount of memory, you're not going to do a perfect job representing all numbers in the infinite and infinitely dense real number domain. Okay? But you just assume that there's enough bits dedicated to fractional parts that you can come close enough without it not really impacting what you're trying to do. Okay? You only print it out to 4 decimal places or something, and it just looks like it's perfect. Okay? Does that make sense? It turns out if I do it that way, then addition works fine. So I add 2.5 contributions and it ripples to give me a 1 and I carry a 1. It just works exactly the same way. Does that make sense? Okay. It turns out that this is not the way it's represented, but it is technically a reasonable way to do it. And when they came up with a standard for representing floating point numbers, they could have gone this way. They just elected not to. So what I'm going to do now is I'm going to show you what it really does look like. It's a very weird thing. But remember that they can interpret a 32-bit pattern any way they want to as long as the protocol is clear and it's done exactly the same way every single time. So for the 20th time today, I'm going to draw a 4-byte figure. I'm going to leave it open as a 4-byte rectangle because I'm not going to subdivide it in bytes perfectly. I am going to make this a sign bit because I do want to represent, I want negative numbers and positive numbers that are floating point to have an equal shot at being represented. Okay? That's one of the 32 bits. Does that make sense? The next 8 bits are actually taken to be a magnitude only. I say it that way, I should just call it an unsigned integer from here to there. Okay? And the remaining 23 bits talk about contributions of 2 to the negative 1 and 2 to the negative 2 and 2 to the negative 3. Okay, this right here I'm going to abbreviate as EXP, and this right here I'm just going to abbreviate as .xxx. Okay? What this figure and how it's subdivided, it's trying to represent this as a number. Negative 1, I'll abbreviate this as S, to S right there. 1.xxxxx times 2 to the 128, I'm sorry, hold on a second. EXP minus 127. Okay, that's a little weird to kind of figure out how the top box maps to the bottom one. What this means is that these 23 bits somehow take a shot at representing 0.0 perfectly, as it turns out, to something that's as close to 0.99 bar as you could possibly get with 23 bits of information. When these are all ones, it's not negative 1. It's basically 1 minus 2 to the 23rd. Does that make sense, everyone? Okay. That is added to 1 to become the factor that multiplies some perfect power of 2. Okay? This right here ranges between 2 to the 8th, 255 and 0. Does that make sense? When it's 255 and it's all ones, it means the exponent is very, very large. Does that make sense? When it's all zeros, it means the exponent is really small. So the exponent, the way I've drawn this here, can range from 128 all the way down to negative 127. Make sense? That means this right here can actually scale the number that's being represented to be huge in the 2 to the 128 domain, or very small, 2 to the negative 127. Okay? Number of atoms in the world down to the size of an atom. Okay? You may think this is a weird thing to multiply it by, but because this power of 2 thing right there really means the number is being represented in the power of 2 domain, you may question whether or not any number I can think of can be represented by this thing right here. And then once you come up with a representation, you just dissect it and figure out how to lay down a bit pattern in a 32-bit figure. Let me just put the number 7.0 right there. Well, how do I know that that can be represented right here? 7.0 is not 7.0. It's 7.0 times 2 to the 0th. Okay? There's no way to get and layer that 7.0 over this 1.xxx and figure out what xxx should be. xxx is bound between 0 and 0.9 bar. But I can rewrite it this way. 3.5 times 2 to the first, rather 1.75 times 2 to the second. So as long as I can do a plus or minus on the exponent, I can divide or multiply this by 2 to squash this into the 1 to 1.9 range, and just make sure that I have to give up if this becomes larger than 128 or less than negative 127. But you're dealing with then absurdly large numbers or absurdly small numbers, but doubles love the absurdity because they have space for that accurate of a fraction. Okay? Does that make sense to people? Okay. So this right here happens to be the way that floating point numbers are actually represented in memory. If you had the means, and you will in a few weeks, to go down and look at the bit patterns for a float, you would be able to pull the bit patterns out, actually write them down, do the conversion right here, and figure out what it would print as. It may be a little tedious, but you certainly could do it, and you'd understand what the actual protocol for coming from representation to floating point number would be. Okay? Let me take the last 10 minutes and talk about what happens when you assign an integer to a float, or a float to an integer. Okay? I'm going to get a little crazy on you when the code I write, but you'll be able to take it. I have this int I is equal to 35. Actually, let me choose a smaller number. Let me do just 5 is fine. And then I do this. Float f is equal to I. Now you know that this, as a 32-bit pattern, has lots of zeros, followed by 0, 1, 0, 1 at the end. 4 plus 1. Okay? Make sense? When I do this, if I print out f, don't let all this talk about bits and representation confuse the matter. When you print out f there, it's going to print the number 5. Okay? The interesting thing here is that the representation of 5 as a decimal number is very, very different than the representation of 5 using this protocol right here. So every time, and not that you shouldn't do it, but every time you assign an int to a float, or a float to an int, it actually has to evaluate what number the original bit pattern corresponds to, and then it has to invent a new bit pattern that can lay down in a float variable. Does that make sense? This 5 is not, the 5 isn't 5 so much as it is 1.25 times 2 to the second, okay, as far as this is concerned right here. So that 5, when it's really interpreted to be a 5.0, it's really taken to be a 1.25, right? Yeah, times 2 to the second. So we'd have to choose exp to be 129, and we'd have to choose xxx to be 0.25. That means when you lay down a bit pattern for 5.0, you expect a 1 to be right there, and you expect 1,000,000,001 to be laid down right there, 128 plus 1. Does that make sense to people? You got to nod your head, or else I don't know. Okay? This is very different, and this is where things start to get wacky, and this is what 107 is all about. If I do this right here, int I is equal to 37, and then I do this, float f is equal to asterisk, you're already scared, float star ampersand of I. I'm going to be very technical in the way I describe this, but I want you to get it. The example above the double line, it evaluates I, discovers that it represents 5, so it knows how to initialize f. Does that make sense? This right here isn't an operation. It doesn't evaluate I at all. All it does is it evaluates the location of I. Does that make sense? Okay. So, when the 37 with its 1 and 0s represented right there, this is where I is in memory. The ampersand of I represents that arrow right there. Okay? Since I is of type int, ampersand of I is of type int star, raw exposed address of a variable that's 4 bytes that happens to be storing something we understand to be an int. And then we seduce it momentarily into thinking that it's a float star. Okay? Now, this doesn't cause bits to move around saying, oh, I have to pretend I'm something else. That would be I reacting to an operation against the address of I. Okay? All the furniture in the house stays exactly the same. Okay? All the 1s and 0s assume their original position. They don't assume. They stay in their original position. It doesn't tell I to move at all. But the type system of this line says, oh, you know what? Oh, look, I'm pointing to a float star. Isn't that interesting? Now I'm going to dereference it, and whatever bit pattern happened to be there corresponds to some float. We have no idea what it is, except I do know that it's not going to be 37.0. Okay? Does that make sense? In fact, it's small enough that all of the bits for the number 37 are going to be down here, right? Leaving all of these zeros to the left of it. Okay, so if I say stop and look at this 4-byte figure through a new set of glasses, this is going to be all zeros, which means that the overall number is going to be weighed by 2 to the negative 127. Make sense? There's going to be some contribution of 1.xxx, but this is nothing compared to the weight of a 2 to the negative 127. So as a result of this right here and this assignment, if I print out f after this, it's just going to be some ridiculously small number, because the bits for 37 happen to occupy positions in the floating point format that contribute 2 to the negative 23rd and 2 to the negative 20th and things like that. Okay? Does that make sense to people? Okay. So this is representative of the type of things we're going to be doing for the next week and a half. A lot of the examples up front are going to seem contrived and meaningless. I don't want to say that they're meaningless. They're certainly contrived because I just want you to get an understanding of how memory is manipulated at the processor level. Ultimately, come next Wednesday, we're going to be able to write real code that leverages off of this understanding of how bits are laid down and how ints versus floats versus doubles are all represented. Okay? I have 2 minutes. I want to try one more example. I just want to introduce you to yet one more complexity of the C and C++ type system and all this cached business. Let me do this. Let me do a float f is equal to 7.0. And then we do this. Short s is equal to asterisk short star ampersand of f. Looks very similar to this, except there's the one interesting part that's being introduced to this problem is that the figures are of different sizes. Okay? Here I lay down f. It stores the number 7.0 in there, and that's the bit pattern for it. Okay? The second line says, I don't care what f is, I trust that it's normally interpreted as a float, and that's why I know that this arrow is of type float star. Oh, let's pretend, no it isn't anymore. You're actually pointing that arrow we just evaluated, it wasn't pointing to a float, we were wrong. It's actually pointing to a 2-byte short. So all of a sudden, it only sees this far. Okay, it's got 20/40 vision. And this right here, this arrow gets dereferenced, and as far as the initialization of S is concerned, it assumes that this is a short. It assumes that this is a short, so it can achieve the effect of the assignment by just replicating this bit pattern right there. Okay, and so it gets that. Okay, and whatever bit pattern that happens to correspond to in the short integer domain is what it is. So when we print it out, it's going to print something. 7.0 means that there's probably going to be some non-zero bits right here. So it's actually going to be a fairly, it's going to have ones in the upper half of the representation. So S is going to be non-zero, I'm pretty sure of that. Okay, does that all make sense to people? Okay, that's a good place to leave. Come Monday, we'll talk a bit about doubles, not much. Talk about structs, pointers, all of that stuff, and eventually start to write real code. Okay?